Okay, so welcome to the introduction then of the neurodynamics course. And so what is this about? So I like to call this like, cognition in the wild. And I often use this photo of my kids playing soccer on a, not a soccer field, on some lawn with some other obstacles in there. And I find that a very useful example. And it's a useful example because in this simple situation, you see that something like soccer playing entails almost everything that we usually think of as part of cognition. So for instance, you certainly have attention, a very important. You see intently my son looking at the ball here, and my daughter is also looking at the ball. So attention, as you know, is a sort of a key entry point into the cognitive system, is very important here. And of course, it's supported by gaze as well. And perception is active. It's clearly that these my kids here are perceiving for a purpose. They're looking at the ball, and maybe they're looking sometimes for the goal. They weren't so terribly skillful at the time, but looking for particular goals and tasks in mind, and they're using working memory of the environment to guide that looking. Spin this jargon, this slogan, use the world as its own representation. That will be embodied cognition, but that will be very, very inefficient if at every moment in time you have to do a complete visual search again for an object you might want to direct your action at. So what you really need is to have a good guidance toward where to pay attention, and that will be your working memory of the scene. So where the ball last was, maybe you're using prediction for that. If you hit the ball, you will expect it to be in some other corner, or where the other player will be. So that's already quite an advanced feature of cognition that is only here to support your connection to the world, to the sensory world. And then, of course, you're doing actions, you're doing sequences of actions, you're making decisions about which actions, and not just, you're making decisions like when to kick or where to move. Some of those would be very sensory motor, but maybe even some strategic decisions that might be oriented toward goals. Maybe more skilled players even have something like tactics or an overall plan. They might have a sequential plan of how to play against Manchester United, have a particular strategy and so on. That will be a level of cognition that's rarely being understood so far in neural terms. And then, of course, downstream, ultimately, you have motor control. You really have to send signals to your muscles to deal with the movement with a yielding soft ground, planning impact. Our robots are very bad at that currently, which reveals how profound some of the problems are. So, robots or computers are good at chess and even Go, but still not very good at this kind of mechanical intelligence where you understand the parts of the world that are hard to model, like how resistive, how slippery the ground is, and things like that. And that's where background knowledge enters. Background knowledge is essentially what classical AI struggled with, all the knowledge about the world that informs the solutions to problems. And that includes a lot of this knowledge that I was just hinting at that is not easy to model, like the impedance of objects and how rough to tackle your sister and things like that. Not just the knowledge that classical AI people try to formalize through informational descriptions, through information processing kind of concepts. And lastly, people learn from experience. And when you play soccer like that, you get better. Even if you don't plan to get better, you just automatically get better at many levels, perception in terms of motor control, or even in terms of goal achievement and so on. Not saying that everyone will be brilliant, but learning always takes place, automatically takes place. And so these are all hallmarks of the most central cognitive functions that we expect people to be able to do. And because they take place in this sensory motor context, they inherit properties from the sensory motor domain. So for instance, for sensory motor domains, it's very natural and obvious that you need somehow graded states, that you can't just work with discrete categorical states. You have to vary the amount of acceleration or the exact gaze angle, or maybe an estimate of where the ball is has to be represented by a graded variable, because it's a graded thing by itself. And these things happen in continuous time, right? It's not an iterative process where you say decision and now I do the next thing, but you're continuously tracking and continuously tuning your actions to perception. And all of the things that you do actively by your nervous system can be linked continuously or intermittently to sensory motor processes. You don't rarefy that interface. It's actually a rich interface. So that actually turns the question around. A lot of classical approach to cognition have thought about cognition as computation, where there's some inputs and then decisions, events occur, and you make an inference and decide something and so on. And that's just taken as a given that that's somehow what you do. And the laboratory experiments, like reaction time experiments, are organized to promote the occurrence of these kind of discrete events. But in reality, these events emerge from underlying continuous behavior, both in terms of time and in terms of the contents of the behavior. And so the challenge arises to understand how these discrete events and the core categorical behaviors emerge from these underlying continua, and rather than just restrict your description to such events. And so think about the rest as an implementation detail. All of this happens in closed loop, and in closed loop it just means that the consequences of any actions and decisions are matter, that for instance, they change your perception, that you perceive something because you acted on it. When you move around, that is naturally the case because the image on your retina will depend on how you moved, but that's also, of course, true when you affect objects in the world. It is in some sense also, I will be arguing later, true internally in your nervous system, where one process changes the inputs to another process. And closed loop means stability requirements. This is something that I will be elaborating in the course, but it's intuitive to anyone who, in engineering or physics, who deals with real systems. You know that when you act on a system that is acting in closed loop, you have to make sure that the way you interact with that system is stable. And roughly stable means small change, small change in the inputs, small consequences. So reacting in a graded way to perturbations. So for instance, when you learn to drive a car, you learn that stability is that as you drive and your car veers off the road, you react in a way that brings it back onto the road. And initially, you're not very good with that. Maybe you're not reacting enough and you're drifting off too much, or you overcompensate and your car starts to oscillate. Hopefully that didn't happen to you. But when you learn a skill like that, you see that stability is an acquired property of your behavior. It is not automatically there. You can react in a logically consistent way to inputs, but be unstable. For instance, logically consistent would be to always counteract the perturbation, but if you don't do it right, then you're overcompensating and you're becoming, falling off the road because of your own compensatory action. So stability is a necessary property, and it is a property that has to be actively given to your system. And so the implication is that that these kinds of constraints from the sensory motor domain matter when we look at cognition. So one could say the big theme of how we will be approaching cognition here in the neurodynamics framework is to say cognition is more like soccer playing than like chess. That is, and by that I do not mean what some people have referred to as saying that when you're thinking, like even in chess, when you're thinking that there's automatic activation of some of your muscles and you always have a little bit bodily consequence of what you do. There are some hints that sometimes might be the case, but it's not clear if it is really mandatory and if it's even a major influence. I actually mean something more abstract, that the processes that underlie cognition are constrained by their sensory motor origin, both evolutionarily, developmentally, and in terms of how they are actually physically implemented in the brain. And that means that the cognitive processes inherit these properties of embodied cognition. So we'll argue in this course that stability properties and then the systematic breakdown of stability under some circumstances are central to even rather high-level cognitive processes. And we'll see how we get in the course. So that implies that there is no that position, right? That hypothesis means that we say there is no real difference between sensory motor ultimately and very high level of cognition that I call here computational or symbolic, which is consistent with what we know about neurophysiology. It's not like somewhere in the brain you suddenly see everything is different. The frontal brain suddenly, it looks like a computer, while the visual and motor cortex look like sensory motor machines. No, everything in the brain looks like sensory motor machines, and that's sort of the neurophysiological argument for this continuity hypothesis. And it's also true in terms of scaling behaviors. You can look at decision tasks where you press buttons and you see sensory motor influences on those decision tasks, even as these decision tasks actually entail, for instance, mental arithmetic or some form of purely mental computation. So that's a little bit the theme, the setup for this course. So the logic will be that closed loop requires dynamical systems. Now, I haven't defined what that is, and I'm not going to do that right away. But here are just two slides that illustrate two types of dynamical systems we'll be confronting. Dynamical systems, again, I'll explain what that is later, have state. So they say that there's something that creates the continuity across time of a process. That's the state, and what we call behavioral dynamics would be close to what engineers think of as control dynamics. That's where the state is a physical state. For instance, here a vehicle is oriented in a particular way in the world, heading to a source, and the fact that it's oriented that way stores, in some sense, its decision to go to that source and not to the other source. And we'll look next lecture at simple ways of how that can be understood in terms of dynamics. Dynamics will be that the rate of changes of variables and the variables themselves are in a functional relationship. So I'm not explaining that now, although some of you might be able to guess it. The other kind of dynamics is internal. So if you're just sitting there, this is again a vehicle that's just sitting there and selecting this left source just mentally, just attentionally. It's paying attention to the left source, not to the right source. And that will mean that we'll have some nervous system here, these little lines that are somehow interconnected, that is set up so that it would create an internal state that will be activation patterns, so neurons firing in their brain in a way that stabilize a particular state. For instance, keep activation up for those neurons that stand for this left target, and suppress neurons below threshold for those that stand for the other target. And that purely mental decision would be then stabilized under such conditions, and it would be stabilized with respect to internal loops within the nervous system. That's the two kinds of dynamical systems we'll be talking about. In this course, I will be mostly talking about neurodynamics. I will only very briefly talk about this. In the summer semester, we talk more about this sort of stuff, which is closer to problems in robotics, even though sometimes the behavioral dynamics are also just simulated behavior in the nervous systems or a computer's mind. So what does neural dynamics really mean? I just want to connect here to things you hopefully know. So you know about neurons in theory from neural networks. I'm not sure how some of you might have heard a whole course about that, perhaps the undergraduate course that Zhensheng is now providing, or some other course, and therefore you know the rough theoretical conceptualization, rough in the sense of omitting a lot of physiological detail of characterizing neurons as essentially input-output threshold elements. So they would be elements that some inputs that they get, and the inputs or outputs are all in the same currency. They're all activation or firing rate or some physiological variable like that. So they are summing these inputs, essentially on their dendritic tree. All the synapses create, excuse me, potentials, and these are transmitted to the soma, and that then sums them. And if the some activity is above a threshold as described by a sigmoidal function that goes from 0 to some positive constant here 1, then output is generated to that neuron. So input-output relations are how neurons are conceived. And mathematically, they're just taken to be these kind of functions. And you can concatenate functions like that by chaining neurons in a feed-forward way where the output of one neuron is the input to another neuron, and then you get a feed-forward. We call that feed-forward neural network. So that's a very common picture. That's a picture that a lot of connectionist thinking is based on. And it's still sort of compatible with classical computation in the sense that there is an input, maybe an input pattern, and an output, and your system is described as a function. In classical information processing, these functions took arguments. The arguments would be would express some kind of invariance that only certain arguments are needed, others are not needed, so you're independent of certain arguments, and you can talk about how functions can be concatenated, or they would talk about them being what's the term, nested. Nested function calls would give you some power, and in the connectionist domain, the arguments are sort of fixed by the connection to the input, so you're not as free to provide any kind of argument to the functions, and they will be neurophysiologically grounded, but it's still a similar picture of the function being the functionality of the network being to implement a function. In fact, one theoretical characterization of these feed-forward neural networks is as a universal approximator, which means it's a implementation that can approximate any mathematical function. Now that's the picture, the information processing kind of picture. Now, in neurodynamics, we're really dealing with recurrent neural networks because we're dealing with networks that have an inner state, and the inner state is brought about by the previous output being an input. So the network does not depend just on fresh inputs, but also on inputs that are its own outputs. Here, so we've taken a single neuron that self-excites, for instance, and that would mean that its previous output provides input. And I already talk about time as a previous versus next, because if you didn't introduce time, then there wouldn't be no well-defined output, right? If your output depends on your output, then that's a problem. So the way to resolve that is to say your output at a certain point in time depends on your output at a previous point in time. And so that output at the previous point of time, that will be the state of that network that will be transmitted. So once you do that, you actually immediately have a dynamical system. This will be a discrete time dynamical system that is an iteration equation where there's a current state and you compute the next state based on the current state plus some external inputs. Of course, in the brain, there aren't really discrete update moments like that. We don't have a CPU. That's what a computer is like, right? But a brain is an asynchronous device where the individual neurons, even though they might spike, and you could think of spikes being like events, which are maybe not, but one could think of it that way. But these spikes are asynchronous, so they don't sample a discrete time. They could represent arbitrarily well any time interval. So it's certainly embedded in continuous time. And when you do not look at the individual spike mechanism, you end up with continuous time varying state variables that we call now activation states. And that is actually the mathematical form in which we describe such things. And that's a differential equation. I'll give you this tutorial this afternoon to give a little bit of background on that. So in this differential equation form, the object of evolution is really the rate of change. U dot is the rate of change of activation, and has this characteristic form that I'll be making a lot of fuss later in the course about minus U plus inputs. So rather than the inputs directly determining the output, what the inputs do is they determine the rate of change, and then the output emerges from that. So that's how neural dynamics comes about. So we will be doing this for a lot of neurons, not for individual neurons. In fact, in many cases, we'll say there are continuously many neurons, which we call fields, activation fields or dynamic fields, that are essentially models of the maps that some of you might know exist in cortex, for instance, and in a lot of subcortical structures like colliculus and even hippocampus. So these neurons have meanings. We talk about them being defined over dimensions that have meaning, and that meaning derives essentially from how they are connected to sensory surfaces, how they receive input from sensory surfaces, for instance, in the form of tuning curves or feature maps and things like that, or how they are connected to motor surfaces, how they ultimately project to muscles and generate output. If you think through that on the motor side, you're actually not specifying particular values, but actually dynamical systems of the behavioral kind. So for instance, a reflex loop in the periphery sets up a muscle to create a dynamical system that has an attractor state at a particular muscle length, which then leads to a joint length. And so what the motor cortex, let's say, does is specify that attractor state so that the rate of change of the length of the muscle is a function of the current length of the muscle, has a fixed point that's stable, and you'll be going to that fixed point. That's the posture when you hold your limb in a particular posture, then you have that kind of dynamical state. And some of you have seen that in the summer semester. In the winter semester, I'll not talk much about this periphery, but I'll talk about these inner states. So dynamical fields are populations of neurons that get their meaning, that is, they are over certain dimensions through their forward connectivity, but that they get their dynamics through recurrence. And the recurrence will be, we call that kind of recurrent connectivity within these inner layers sometimes interaction. So a physics term, but it's really just another term for recurrence when it's used in this particular way as creating stable states. And what will be most important is some universal form of interaction that we'll often see, where activation variables, or neurons if you wish, that are neighbors in the field. That means that they are connected to the sensory or motor surface in a similar way as their neighbors, that they tend to be excitatorily coupled. So once they fire at a positive activation level, they induce their neighbors to also fire. So that stabilizes localized activation patterns against decay. And then the second kind of interaction is where over longer distances, so for neurons or activation variables that represent more dissimilar things, they tend to be inhibitorily coupled. That is, if one of them fires, it suppresses the other one, and vice versa. And because of the sigmoid characteristic, which is still true for the interaction as well, that is only neurons that fire, that are sufficiently activated, produce any output, and only those kind of outputs can actually be inputs to other parts of the neural network. Because of that, this is sort of asymmetrical. That is, if you have a peak that fires, it can suppress activation elsewhere, but that suppressed activation cannot conversely suppress the peak. And that's how systems like that can make decisions, selection decisions, bringing up a peak in one location and suppressing peaks elsewhere. So that will be the core of the course. We'll be talking about these populations of dynamical neurons. That's what we will call neural dynamics. That's what's in the title of the course. And we're going to these fields because we're looking at that at the central levels, what we call the cognitive level, where decisions are made and so on. While in the periphery, for instance, if you go very early from the retina up to maybe LGN, visual cortex, or early psychophysics associated with that, similar for the auditory system, for haptics. And then again, if you go, let's say, from the spinal cord down, where slightly different things happen, that's where the rates of firing play a role. And so on. Here's more the location of activation patterns in the brain that matters. I'll have something to say about that 2 lectures down or 3 lectures down on neural coding. But the course will be primarily about the central level, not so much about the periphery, which is the emphasis of a lot of other teaching. So summarizing, what we do then with this way of thinking is 3 kinds of research programs. So a theoretical research program that this course is largely trying to introduce you to, and that's essentially a theory of behavior and thinking. I'm saying behavior in the sense ultimately sensory motor behavior that we want to understand, and thinking as its extrapolation, as I just hinted at here, where in some continuous way the tie to the sensory motor surfaces can become less and less direct and more abstract. And as that happens, we call that then cognition. It's still embodied because it still has that connection, but it can ultimately take forms that are no longer really necessarily acted out on. For instance, like when you do mental inference and you don't actually have to act on it right away. So that's kind of theoretical program is what, developing a theory for that, that's the basis of which are taught in this course. And that amounts to providing what we call process accounts for cognition and other aspects of behavior that are based on neural principles. And by process accounts, we mean, I'm going to explain that more in the course, we mean accounts that really can generate the time courses of inner state variables or ultimately also motor state variables that will generate the behavior, so that if we can mathematically realize the solutions of the corresponding models, we can actually drive actual hardware. We can drive a robot. That's what we sometimes put on robots. A robot to behave like an organism. That means we explain really how these principles lead to the behavior, are generative. As contrast, let's say, to theories of cognition where you would just describe the cognition. For instance, you can say, how does the reaction time depend on the complexity of the task? And then you have a curve that predicts that, but that curve itself does not, of course, generate the decision-making behavior. It just describes it, right? And process accounts would go beyond description, would actually generate it. And generate it, a computer program also generates something, but generate it in a way that is linked to neural principles of how neurons work, but at a certain level of abstraction. So maybe not going into all the details of the neurotransmitters and the membranes, certain description of how neurons work that abstracts from some of those details. So when you do that, you're looking at behavior and thinking in a certain way. I talk here about naturalistic tasks that connect to elementary behaviors and elementary forms of cognition. That is, what is elementary here is, again, part of the theory. You have to say what elementary is. So, for instance, we'll be making a lot of fuss about detection decisions and selection decisions. We'll say those are elementary. And then naturalistic refers to that. That is, that you're saying, what is a typical embedding of a, for instance, a detection decision, and to contrast that with tasks that are often used in the more classical literature that are very local in the processing, where you're taking a very limited interface. For instance, you have some abstraction of a sensory signal and some abstraction of a decision variable, and then you say signal detection theory, for instance, predicts the probability of you detecting something. And we will do something much more integrative, where we take it all the way down to sensory processes and all the way down to motor processes to account for behavior. In that respect, naturalistic tasks, for instance, very often have the sensory motor embedding of the task. You will see that as we go along the course. So this research program, it might be, this is an introduction. It might be a little mysterious now, but at the end of the course, you're supposed to understand the nature of that research program. We'll talk less about the associated experimental research program, but I will be pointing to that. So it's a program that is aimed at providing evidence for these theoretical concepts, and that actually is also providing this set of phenomena that we want to explain. So in one, coming from the theory, it would be framed as looking for behavioral signatures of the postulated principles. And I'll take you through some of those examples. Very often we'll look at metric effects, or how effects depend in a graded way on certain variables, on the role of time, the role of context, the role of intermittent linkage to sensory inputs, or what we call online updating. And we'll also be very much interested in establishing links between different component processes, the part that is not so well studied in classical fields. But you can also actually approach this from the other side and say, here's a whole set of phenomena, like some of these embodiment phenomena, and try to understand them. And then this theory would help you understand them. That's not so much the perspective I will be taking. And the last component of that program is robotic demonstrations, which in the winter semester I'm doing only in a very limited form, but that's again the core of the summer semester lectures. So we're talking about autonomous robots, that is, robots that generate behavior based on their own sensory information and act on that information with its own actuators, and does cognitive things, that is, takes decisions, initiates action. So it's not just transducing commands that are given from the outside to that system. And such autonomous robots, in a sense, are some model systems of organisms. And so if we understand the organisms through neural principles, and we can use the robots as of implementations of organisms. And so sometimes we're using these autonomous robots as heuristic devices that demonstrate that our accounts are true process accounts. And that's really the use of robotics. You know, robotics as a technical field uses all kinds of approaches. There's no priority, a priority to neural methods. In fact, it's special subcommunity only is interested in neural methods. Through deep learning, currently neural methods are again very fashionable, but that comes and goes. So again, I will not be talking so much about it in this in the winter semester, but it's sort of in the back of our minds always, because we're always thinking about how would it be ultimately driven by sensory inputs. And so sometimes in some of our models, we actually use real camera input from a scene that is filmed as what drives our models. And we do that really just to check that that works, that there's nothing that we didn't abstract from, you know, make abstractions that are very costly. So for instance, you have some models that account for things like object permanence in infancy, just as an example. And then they have a neural network model where one neuron stands for one object. And that's not something you can easily implement on a robot, because that means that the whole field of object recognition and segmentation, localization, pose estimation, all of that is taken for granted. That somehow, magically, some neuron always fires when there is, you know, this particular object in the visual array. And so that's not what we want to do. And the robotics are a way of keeping our feet on the ground with respect to that. So in that sense, I'll also be referring to these kind of ideas in the winter semester. Good. So what do you learn in this course? Well, you learn some elements of that embodied cognition. We'll learn about detection, selection, working memory will be important. The memory trace will be important. You will learn the theoretical concept of this form of neurodynamics. I already hinted, you know, what behavioral neurodynamics are, dynamic neural fields, and the concept of the field theory that include, I'll come to that in a moment, that are neurally grounded. So you learn some basic neurophysiology. You learn it really from the point of view of a theoretician. Rate code, neural maps, population code are more or less theoretical ideas. Experimentalists are not even so keen sometimes on them. I might give you a little introduction to neurophysics more as a side aspect, you know, the dynamics of membranes. You'll learn some mathematical concepts, dynamical systems. You'll learn something about that, about attractors, stability, instabilities, when attractors lose their stability. You'll have some idea about how differential equations are solved. Numerically, we'll not go into any sophistication about that, but that will be part of our language. And you will learn a little bit about how theories like that, theory of behavior and cognition, can be linked to neural and behavioral data, and what it means to account for behavior in terms of process models. So we'll not talk much about robotic and simulated behavior, but you'll learn a little bit about that. So that's the contents. And then academic skills, well, you're learning you know, to read and understand scientific texts that are not in your main field. So that is makes it more interesting, more challenging, and to write about such problems in a technical way that uses mathematical concepts and illustrations. That's a real skill that you learn. So the mathematical skills are more, again, conceptual, understand dynamical systems, to not be mentally blocked when you see a differential equation, to understand them in some way, to see patterns in them, to illustrate them, to draw, you know, to be able to say, what does it mean to plot a dynamical system? What do you mean, what that means? In some sense, you will be learning to do mental simulations, that is rough predictions, very qualitative kind of predictions about what the solutions of a differential equation would look like. It's all based on attractors. And a little bit to test numerics, although we'll have a few exercises where you actually play with a simulator and see that numerical work in modeling is like experimental work, where you have to have hypotheses and test them and so on. It's actually a whole field, but we'll only be learning this a little bit. This is not a course that's primarily giving you that kind of skill. And then maybe the most important is this interdisciplinarity. You will learn to handle concepts from different disciplines, which always means that you have to handle things that you don't understand. And that is actually a very important skill. It's a skill of better metacognition, better knowing what it is that you know, what you don't know, distinguishing that more clearly. You know, if everyone around you has the same concepts and the same prejudices, doesn't even it's not even noticed if you don't really fully understand, because you're just buying into the frameworks of others, and automatically someone else has thought through it and you don't have to. But in interdisciplinary work, the others don't share that framework, and you're responsible for making sure things make sense in your framework. And that is a special skill. It actually really advances your understanding of your home discipline if you engage in interdisciplinary interaction in that way. And that is a very important skill today. You know, in academia, you know, it's important in that a lot of innovation comes from interdisciplinary research, but it's actually more important in the real world. In the real world, you'll always have constraints from all kinds of different fields. You know, I have accounting people and marketing people and technical people and, you know, creative people, and people who maybe adjust the products to different audiences and are very informed about cultural issues and so on. And all of those people have different backgrounds, and they converge on a product, for instance, or a certain business process. And you have to have exactly that kind of skill. You need to know what your territory is, how to achieve some level of understanding of a discipline you don't fully understand, how to deal with stuff you don't know, how to make judgments and get trust. And it's a whole, it's an attitude that is certainly removed from the image, for instance, the image of the nerdy engineer who would just talk among engineers, or who would, the computer scientist who would only live in the code. That's very far from reality, and it's a very important, I mean, you have to have your own skills, but it's a very important component of success is to be able to interact with people from other disciplines to communicate well. And so in that sense, it's a very general skill that you'll be learning in one particular context. Good, that finishes my